Okay, let me rewrite the two equations which we obtained from the previous pages. A1 plus B1 is equal to A2. This was our equation 1. And then we obtain Z1 into A1 minus B1 is equal to Z2 into A2. This is our equation 2. Okay, and if it is a string which is fixed at both ends, then Z1 is the impedance of the string and Z2 is the impedance of the other medium which we use in order to fix the other end of the string. It may be your hand or it may be any other thing. Okay, so Z2 is basically the impedance of that part of the medium through which the wave transmit. A part of the wave reflect and a part of the wave will transmit. Okay, so Z2 is the impedance of the medium when the wave transmit through that part of the medium. Okay, suppose if you lose held the other part of the string loosely, then one part of the wave will transmit through your hand. Okay, so that part of the impedance we call it as Z2. Okay, so A1 plus A2 is equal A1 plus B1 is equal to A2 and Z1 A1 minus B2 is equal to Z2 into A2. Okay, now what we are going to determine, we are going to find out the value of B1 over A1, which give us the reflection coefficient, and then A2 over A1, which will basically give us the transmission coefficient. Okay. Okay. Now from 1 and 2 we can easily determine the value of B1 by A1. For that, what we need to do, we need to just replace A2 with A1 plus B1 in this expression. Okay, so replacing the value of from equation 1 into what we will obtain, Z1 into A1 minus B1 is equal to Z2 into A1 plus B1. Okay, so it will give us what I am going to do, I am going to take this factor common. So Z1 minus Z2 will into A1 is equal to Z1 plus Z2 into B1. Okay, so B1 over A1 will give us Z1 minus Z2 over Z1 plus Z2. Okay, so this is the value of our reflection coefficient. Okay, we can obtain many important results from this expression. For example, if Z2 is infinity, okay, that means suppose this part of string is so tightly held that there is not any possibility of wave transmitting through this part. That means Z2 is equal to infinity, and in that case Z1 minus Z2 almost will be equal to Z2. So that Z1 is infinity, that means Z1 is very greater than Z1. Okay, so that means Z1 minus Z2 almost equal to Z2, and Z1 plus Z2 almost equal to Z2. Okay, so in that case B1 over A1 is equal to minus 1, that is B1 is equal to minus A1. Okay? The physical meaning of this statement is that the wave which is incident at this boundary, it will get totally reflected back, having a phase difference of pi or 180 degree. Okay, so if in such scenario, when B1 is equal to minus B2, the incident and the reflected waves are 180 degree out of phase. Okay, this is the physical meaning of B1 minus B2. Okay, and when such type of wave superimpose, then what we will obtain is the standing wave. We are going to study the standing wave in this course. So standing waves are obtained when the incident and the reflected wave superimpose with the phase difference between the reflected and incident wave being 180 degree or pi radian. In such cases, we are going to get the standing wave. Okay, and this is our case 1. Case 2, if the other end of the string is free, if the other end of the string is free. In that case, what will be the value of Z2? Z2 will be equal to 0 because there is no impedance to the propagating wave as this end is free. Okay, so then what we will get, B1 over A1 is equal to 1. That is B1 is equal to A1. Okay, so this is this is analogous to the condition which we can term the flick of the string, the flick at the end of the string, Okay, so this phenomena you could have observed. Just put a string and just try to vibrate it without fixing it other end. Then when the incident wave will reach at the end of the string, then it just flick around. Okay, the string will flick around, and that is possible because our incident wave is now exactly in equal to the reflected wave. There is no phase difference between these two. Okay, so this is analogous to the flicking at the end of the string. Okay, so these two special cases we can consider with this expression of reflection coefficient. When Z2 is equal to infinity, that means the reflected wave will suffer 180-degree phase shift, and when such type of two waves superimpose, what we are going to get is nothing but the formation of a standing wave. On the other hand, when the other end of the spring is free, that means Z2 is equal to 0, then incident wave and the incident wave and the reflected wave, they will have the similar kind of phase, and what we will observe in that case, there will be the flicking around of the string as the incident wave reaches at the loose end of the string. Okay, so these two cases we will consider in the later part of the course. First, here we have just derived the condition when to get such type of a standing wave or flicking around of the string. Okay, so next what we are going to determine, we are going to determine the transmission coefficient. The transmission coefficient is nothing but the ratio of A2 by A1. So in the expression, we have to replace the value of B1. And B1 is equal to, we know that B1 by A1 is equal to this value. So from there, if we replace the value of B1 here, we can easily get the ratio of A1 by A2 by A1. So let's do it. We know A1 plus B1 is equal to A2. Okay, so again we know that B1 by A1, which we have just derived, Z1 minus Z2 over Z1 plus Z2. So B1 will be equal to Z1 minus Z2 over Z1 plus Z2 into A1. Okay? Just we have to replace this value here. That means we will get A1 plus Z1 minus Z2 over Z1 plus Z2 into A1. In place of B1, we will write like this, is equal to A2. Okay, if we take A1 as a common factor, then it will be 1 plus Z1 plus Z2, Z1 minus Z2 is equal to A2. Therefore, A2 over A1 is equal to how much? It will be Z1 plus Z2, Z1 plus Z2 plus Z1 minus Z2. Z2 cancel out. It will get 2Z1 divided by Z1 plus Z2. Okay, so A2 by A1 is equal to our reflection, transmission coefficient. So now consider the case when Z2 is equal to infinity. When Z2 is equal to infinity, as we can see, this part is something divided by infinity will give us 0. Therefore, A2 will be equal to 0. There is no transmission of wave. No transmission of wave. as one expected, because our impedance of the second part of the medium which we used in order to fix the other end of the string is now infinity. That means the wave cannot transmit through that medium at all. So this condition we have derived as A2 is equal to A2 by A1 is equal to 0. That is no transmission of wave through that medium. Through that medium. Okay. So in this way we can derive those important conditions once we consider this reflection and the transmission coefficient. Okay. So this thing you have to remember, A2 by A1 is equal to 2Z1 over Z1 plus Z2, and B1 over A1 is equal to Z1 minus Z2 divided by Z1 plus Z2. Impedance of the string Z1 and Z2 is the impedance of the other part of the medium which we used in order to fix the string, or through which the the transverse wave propagate. Okay. So with this I came to the conclusion of this part of the lecture. Next we are going to consider what is the amount of energy transmitted by incident or the reflected wave. Okay. And the energy transmission by incident, reflected and transmitted wave. How much energy this such type of wave carries. Okay, so that I'm going to do in the other part of the video. Thank you. Good morning, student. Welcome to the second part of the video. Here we are going to determine the energy of incident, reflected and transmitted wave. Okay. So we know that the average energy which the wave carry in case of a transverse wave, it is given by half into rho, as you can remember, omega square into a square. So this is the average energy which the wave transverse wave carry. Whether it's a incident wave or reflected wave or transmitted wave, it doesn't matter. This is the amount of average energy carried by the wave. Okay. Now what we are going to do, we are going to relate this expression with the impedance of the medium, impedance of the string and impedance of the medium through which the wave transmitted. Okay, so we know that the impedance of the string is equal to Z1, and impedance of the medium through which it transmits, impedance of the other medium other than the string, other medium through which it transmits, is equal to Z2. So basically what we are going to do, we are going to relate this expression, energy carried by the wave, with the impedance of the string as well as the other medium through which it transmits. Okay. Now for that we know the energy carried by the wave, average energy carried by the wave is this. So the rate of the energy, if we calculate rate of the energy, then it is basically nothing but average energy multiplied by the velocity of the wave. Okay. So we have to multiply the average energy by the velocity of the wave. Okay, and we, as you can see, the velocity of this part was c1, the incident or reflected wave, and the transmitted wave has a velocity of c2. Okay, so the average rate of incident energy now, rate of incident energy, rate of incident energy will be equal to the energy carried by the incident wave multiplied by its velocity. So energy carried by the incident wave will be half rho omega square, and in this case amplitude was a square, so a square into c. And this value we know. Okay, but we know that rho c is nothing, rho c1, sorry, rho into c1 is nothing but the impedance. As I have already find out, z1 is equal to rho into c1. So in place of rho into c1, what we can write as z1. So this value is equal to half z1 omega square into a1 square. This value we can find out. This is the rate of incident energy. Okay, similarly the rate of reflected energy, what will be its value? Half into rho omega square. Reflection coefficient was b1, so it is b1 square into c1. It was c1 because in this part the velocity was c1 and other medium the velocity was c2. Okay, so we can write half again z1 omega square into b1 square. This is the rate of reflected energy. Then rate of transmitted energy, this value is equal to half rho omega square. In this case, let me write this rho 1 and this is rho 1. And we put that Z1 is equal to rho 1 into C1. Rate of transmitted energy, the other part of the medium has a mass density is equal to rho 2. So half rho 2 omega square into the coefficient was A2 square into C2. Okay, so rho 2 into C2, we can put it as Z2. Since Z1 is equal to rho 1 C1, rho 2 is C2, we can put it as Z2. So this value will be equal to half into Z2 omega square into A2 square. This is the value of the rate of transmitted energy. Okay, so now according to the energy conservation principle, incident energy must be equal to the reflected plus transmitted energy, because after all one part of the incident energy will be reflected and other part will be transmitted. So what we can prove that half into Z1 omega square into B1 square plus half into Z2 omega square into A2 square. This is the rate of reflected energy plus rate of incident energy. This must be equal to which value? Half into Z1 omega square into A1 square. Okay, because this is according to the principle of conservation of energy. So I put it as a homework to prove that this part, the left hand part of the equation, that is half into Z1 omega square into B1 square plus half into Z2 omega square into A2 square. This when you do this calculation, you have to show that this value is equal to half Z2 omega square into A1 square. Okay, for that what you need to do, you need to just substitute the value of B1 and A2 with respect to A1. For example, we have already determined B1 by A1 as we determine Z1 minus Z2 divided by Z1 plus Z2, is not it? Similarly, A2 by A1 we have determined it as 2 into Z2 over Z1 plus Z2. Okay, so what you need to do, you need to substitute the value of B1 as Z1 minus Z2 divided by Z1 plus Z2 into A1 and A2 as 2Z2 over Z1 plus Z2 into A1 and substitute here. Okay, once you substitute those things here, you are going to get this expression half into Z1 omega square into A1 square. So you have you should be 100% sure that this have to be this equal to this value, because any physical system has to obey the law of conservation of energy principle. Here we have neglect all the loose mechanism present in the string system. Therefore this quantity must have to equal to this quantity. Okay, so I put it as a homework problem in order to show that this quantity is exactly equal to this value. Okay, so in the next part, what we are going to discuss, we are going to discuss about the formation of standing wave on the string. Okay, this part I think you have already done in your higher secondary level. Now here we are going to derive those expression for standing wave. Once we do the standing wave for the string, we'll again proceed to find out the standing wave in longitudinal wave. As you know, the string wave is a transverse wave. So in transverse wave, there is a possibility of standing wave formation. Then it should be also held true in longitudinal wave. Okay, so in the next part of those lecture, we are going to basically concentrate on the formation of standing wave on string system as well as longitudinal wave system. For example, the sound wave. For those kind of wave can also show the formation of standing wave. Okay, so next part we are starting with the formation of standing wave.